Good morning to all of you. Am I audible? Am I audible to you? Please, anyone reply me. Am I audible? Monali, am I audible to you?
Yes.
So today we would be learn quadrature amplitude shift keying technique or quadrature amplitude modulation. So we are learning the passband signal modulation. So in this case, we have learned lots of the technique ASK, BPSK, FSK, and MRE, PSK, MRE, FSK as well. So generally in BPSK, QPSK, and MRE, PSK, we transmit in any symbol interval one signal or another, which are distinguished from one another in phase, but are all of same amplitude. So in the PSK techniques, generally the amplitude is same and frequency is same, only phase it changes, okay, from symbol to symbol. In each of these individual systems, the endpoint of the signals vectors in the signal space diagram falls on the circumference of the circle, because amplitude is constant. That's why it is only falls on the circumference of a circle, that we have also learned yesterday as well. Now we have noted out that our ability to distinguish one signal vector from the another in the presence of noise will depend on distance between the vector endpoints on the signal space diagram. Like QPSK, it involves the balance modulation of carriers in quadrature, and hence might be abbreviated at the QASK also. However, accepted abbreviations of QASK or more simply quadrature amplitude modulation. So what is actually happening in this QPSK, QASK? We are modulating amplitude as well as the phase, both in a same modulation technique. Till we have only doing the modulation of either amplitude or phase or frequency only, but in this technique we are going to modulate both the signal on a same modulation technique. Means the amplitude of the signal is also varied as well as the phase of the signal. That is called the quadrature amplitude modulation or quadrature amplitude shift keying. Both name is common. So if you have to be see geometrical representation of this QASK or QAM, so you can see here we have to be use the combining of the 4 points, 4 bits, means it would be having the 16 symbols. In the QPSK, we are combining the 2 bits and we are generating the 4 symbols. But here we have to be combining the 4 bits, and that would be 2 raised to the power 4. 16 symbols are possible, and that 16 symbols has been shown in this particular signal space diagram, where x-axis is in phase channel and y-axis is a quadrature channel, and that is having the amplitude of either A or 3A. The signal vectors having the amplitude either the A or 3A, and we have represented 4 symbols on each quadrant. The representation of these symbols would be depends upon the choice of user. There is no any fixed pattern. You can use any of the pattern, means either you can represent in phase and quadrature component or 4 combination on a one quadrant. In the different second quadrant there is a different combination, third quadrant different combination, like this. Or you can also select a simpler way, that your first 2 bits, means MSB and next to the MSB would be fixed from left to right in all four rows, and last two bits means LSB and before LSB would be also fixed for all columns. So that is the way that you can, different methods you can use for representation of this. So you can see here, if I would be refer this diagram that I have taken, so you would be found that first two bits in this first row are common, 0, 0, 0. Okay. Similarly, the second row, 0, 1. And this, in this way, that would be pattern 1, 1, and then 1, 0. Means what happens in every, this is the quadrature component you can consider, that would be 0, 0, 0, 1, 1, 1, and 1, 1, 0 is fixed in all the columns. Okay. In the similar way, if you have to see the in phase components, that is also fixed here. That is 0, 0, 0, 1, 1, 1, and 1, 0. Similarly, 0, 0, 0, 1, and 1, 1, 1, 0. In the similar way, all the four rows has also covered. Okay. So this is the way, one of the way to represent the geometrical representation of the QASK signals. So all these 16 symbols could be represented in the in phase and quadrature channel, and each single vector either having the distance of A from the origin or either 3A. So if you would be like so, please note it down or take the screenshot of this. So you would be found that according to this assumptions, what happens, you would be calculate the symbol energy. So what is symbol energy is here, if you have to be going to calculate, in this configuration, each signal point is equally distant from its neighbor, that is D is equal to 2 of A. That is also very much clear. Between each point there is a difference of the 2A. Either you have to be move into the x-axis or y-axis, it would be only 2A is there. Okay, that is the uniform distance we have kept. So one thing correct here, it is 2 raised to the power 24. It is not 24, 2 raised to the power. Okay, so in this way we can calculate the energy of the signal. That is, if you have to take any of the quadrant, suppose I have taken this first quadrant, so I would be able to calculate the energy of this quadrant. So for this quadrant, suppose, so it would be what is the amount of energy, average energy. It would be found that it would be divided by 4 because there is a 4 symbols. And what is the distance of this? A square plus A square. You can see this first point, this is A square, distance is A here, and also, so if you have to find out the distance from the origin, means this distance, that would be a right angle triangle. So it is A and this is also A. So A square plus A square. Similarly, for this point from the origin, it would be the distance is what? 3A square, means 9A square, and A square. So you can see here 9A square plus A square. Similarly, the another point, if you have to be going to calculate, then it would be, suppose this point, what is the distance is there? 9A square, 9A square, because distance is 3. Similarly, for this point, A square plus 9A square. So this is mentioned here, 9A square plus A square plus 9A square plus 9. In this way, the average energy would be came for the first quadrant is 10A square. That is written as equation 1. Then from this you can find out the value of the A with the help with respect to the energy of the signal. So that is ES upon 10.1 ES square root of the 0.1 ES. This is equation number 2. And in this way we can find out the distance D. D is equal to twice of A. So you have 2 into square root of 0.1 ES. Or you can also write it square root of 0.4 ES, whatever. So note it on this equation, that would be helpful for us to defining the equivalent distance further. Okay. So this gives the D gives the distance between the signal points of the 16 QASK, because here are the 16 symbols. There is a multiple way, 32 QASK, 64 QASK. It is also possible depending upon how many bits you are combining. So we have combined only 4 bits. That's why it is a 16 QASK or QAM technique. Okay. So the normalized energy is what? ES. So ES is basically, if you have to see, it is 4EB. Normalized energy is ES is equal to 4EB, where the EB is the normalized bit energy. Hence, you can write A is as 0.1 ES square root of this, then in this square root of 0.4 EB, and either a distance is there. That is again I have rewritten here. And this distance basically significantly less the distance between the adjacent points in the QPSK modulation, where distance was D is equal to 2 square root of EB. However, the distance is greater than the 16 QASK than the 16 MPSK, Emery PSK. So you can see that in this way, the distance of 16 QASK is less than QPSK but greater than 16 Emery PSK. So this 16 QSK will be shown to have a lower error rate as compared to the MPSK, 16 MPSK, but higher error rate as compared to the QPSK because of this difference of the value of the distance between the signal point. That is the equivalent distance actually. Okay, so this is all about the signal space representation of the 16 QAM technique. Now we have to be see or learn about the transmitter and receiver of this. So for that purpose, we have to be first define the equation of the signal, means modulated signal, that is the VQASK here, or you can either represent it as a ST, that is also a simpler representation. Either of these you can use. Some book use that, and some book use Simon Hacking use ST, and this is using Topsling is VQASK. So basically the equation is say K1 A U1T plus K2 A U2T. So U1T and U2T is what? It is nothing but the orthogonal carrier signals. Means generally we represent phi 1T and phi 2T. And K1 and K2 is here. Each is equal to either +1, ±1, or ±3. That we have seen in the geometrical representation. The distance of the signal points from the origin is either A or 3A. So both in both axes, or positive and negative axis. That's why it is either +-1 or +-3. So in this way, you can define the orthogonal carrier signals as U1 is equal to square root of 2 upon Ts cos omega naught T, or U2 is square root of 2 upon Ts sin omega naught T. That is very much common on all techniques we have taken. And A is the value of square root of 0.1 ES. So we can rewrite this equation number 5 as, that is ST is equal to K1 square root of, just substitute the value of U1 is here and the A is there. So it would become K1 square root of 0.2 ES upon TS cos omega naught T plus K2 0.2 square root of ES upon TS sin omega naught T. This is equation number 6. Now we have to convert the energy signal into the power signal. ES upon TS is equal to what? PS. So here you can write the QASK signal as K1 square root of 0.2 PS cos omega naught T plus K2 square root of 0.2 PS sin omega naught T. Everyone please take the screenshot or note it down this equation. So equation number 7 is here. The equation that we have to be defining for quadrature amplitude modulated signal, QAM or QASK. Okay, so that equation number 7 would be carried out for deriving the transmitter of the QASK, and that would be further seen. I hope all of you have taken the screenshot of this. You have to be move to the transmitter of this QASK. This is the diagram that is tell us about the transmitter of QASK. So this is, you can see that the bit pattern or binary sequence BT is used here, that is entered to the or given applied to the serial to parallel converter, where the data has been entered serially of 4-bit data that we have seen that in the QSK we have combined the 4 bits information with serial to parallel converter having the clock of the after every CS second. So it would be further split it into the 4 parallel bits, that is BK, BK plus 1, BK plus 2 and BK plus 3, that is given a prefixes to this data sequences, and then this 4-bit registers that is applied to the 2 digital to analog converter. So first 2 bit is BK and BK plus 1 is given to the upper digital to analog converter, and BK plus 2 and BK plus 3 is given to the lower digital to analog converter. And a new symbol, if you have to be see that each symbol would be having the time period of the TS is equal to 4 TB. Okay, and this that 2 bits has been presented to the upper and lower digital to analog converters. The converter output would be, here you can see here AET. We have to be use the even and odd notation, so instead of quadrature we have to write like this. So upper one is AET, that is the analog signal corresponding to the first 2 bits, and that would be given to the product modulator, where it would be multiplied with the carrier signal square root of PS cos omega naught t. Then the lower signal, that is output of the digital to analog A naught t, is applied to the second product modulator, where it would be multiplied with the another carrier signal, that is square root of PS sin omega naught t. And upper one is the even function and lower one is the odd function. You can say that that would be output of this product modulator would be given to the one adder, where it would be added, and finally we have to be obtain the QAM output. So the you can see this operation is very much similar to the QPSK and MREPSK. Okay, finally we have to be add these two odd and even functions carriers, and then we have to be obtain the final QAM output. So the transmitted signal of QAM would be nothing but, you can define it as ST is equal to AET square root of PS cos omega naught t or 2 pi f naught t plus A naught t square root of PS sin omega naught t, or like this. This is equation number 8. That would be actually given the information of the, this is nothing but the QAM signal, final QAM signal that would be transmitted to the channel. It is the final QAM signal. Okay, and if you have to be compared the equation number 7, that is also the given the equation for the QAM signal. So equation number 7 and 8, if you have noted down the 7 equation, if you have to be compare this, you can obtain the value of the even symbol and the odd symbol AET and A naught t. So what is the value of AET and A naught t after comparison? It would be came as either plus minus A or plus minus 3A. Means in terms of energy, you can see plus minus square root of 0.2 or plus minus 3 into square root of 0.2. Okay. So that would be the value came out of the even and odd symbols, that is having an amplitude plus minus A or plus minus 3A. That is clear from the geometrical representation. That's why I am told you that first of all I have told teach you the geometrical representation. This is very much important. So also since all 4 values are equally likely, then you can take the amplitude of this A square, or average value of this is nothing but the 1, because all 4 values are equally likely. That is given the equation number 10. So thus each of the quadrature terms in equation 10 conveys on the average one half of the average total transmitted power, because all these four symbols are equally likely. The each of these quadrature component would be having the one half of the average of the total transmitted power. Okay. Now we have to see the QASK receiver. Again, you have to see that in this diagram, the receiver structure is very much similar of the QPSK and the MREPSK. Only the carrier recovery circuit is different, means the band pass filter tuning is different, as well as the limits of the integrator is changed. So you can see here again, if you have to see QASK receiver shown in this particular diagram, where this QASK signal has been be received by the receiver through the channel. So there is it would be given to the two part of this particular structure. First is applied to the carrier recovery circuit, where it would be raised to the fourth power because we have combined the 4 bits, and then it would be passed through the band pass filter having the frequency of cutoff frequency of the 4f0, and if the signal would be having the frequency greater than or less than 4f0, it would be discarded. DC component would be discarded. So finally it would be given to the frequency divided by the 4, and here we have to be finally obtain the carrier signal, that is sine 4 omega naught t and cos 4 omega naught t. Okay, and this would be applied to this product modulator or balance modulator, you can say, and here it would be combined with the received QASK signal. So two component, odd and even component, would be generated. So upper one is the even is and lower one is the odd is there. So here even component and lower one is the odd one. Okay. And it would be further applied to the integrator, where it would be integrate, and AET and A0T would be generated again, and it would be given to the A to D converter. Two A to D converter are used here. That would be further convert this even component of analog signal into the digital bits V0 and V1. That is, we have see BK and BK plus 1, and then A0T would be convert the BK plus 2 or BK plus 2, means B2 and B3. So in this way, we have recovered the or 4 bits, original 4 bits from this receiver structure. Okay. So this is the structure of the QPSK receiver, and this is the function. So it is very simple. I have already told you, I am again repeating. If you have to be remember one of the receiver structure, either is a QPSK or MREPSK, it would be easy to derive the rest of this. So BPSK, QPSK, MREPSK, as well as the QASK is having a similar kind of receiver, only minute changes are there. Okay. Now, after the operation of this, you can see that how this mathematically can be written. Means when it will be passed through the raised to the power 4 circuit is there, then it would be PS square, and then this is term would be there, and then further it would be written as in terms of even and odd components. Okay. So that we have already discussed. Last one is of this particular topic is the spectrum and bandwidth. So this is the spectrum that is very much similar to the spectrum of the QPSK. You can see the signal has been be uniformly distributed around the this y-axis, that is having the time period 1 upon ts and minus 1 upon ts like this. So you can calculate the bandwidth at a difference of these two, that is 2 upon ts, that is 2fs, and here ts is what, n times of the tb. Okay, so in this way you can say bandwidth is nothing but 2 into fb upon n, and depending upon the value of n, if it is a 16 QASK, so n would be what? 4. So it is 2 FB upon 4 or FB upon 2. If it is a some different value of the QPSK, then it would having a different value of the bandwidth. So as the number of bits would be increases, your bandwidth would be decreases. More amount of bit would be combined to create a symbol, so your bandwidth would be simultaneously your bandwidth would be also uh, decreases. Okay, so if you have to be see the comparison of these two signals, generally I have told you that it is very much similar to the QPSK, but here we have to be varied amplitude as well as the uh, phase. So you can compare the two signals, that is QPSK and QASK. This is generally sometimes in the examination they ask the comparison between the QASK and QPSK. So if you have to see the modulation, there's a certain point you can note down like this. One of the point is modulation. So parameters of modulation. So QPSK quadrature phase and QASK quadrature amplitude and phase both. Location of the signal points you have to see in the QPSK, it is signal points are on the circumference of the circle, and in the QASK it is signal points are placed symmetrically about the origin. If you have to see the Euclidean distance, so in the QPSK it is 2 square root of EB for 4 symbols, and for 16 symbols it is 2 into square root of 0.15 EB. But for the QASK it is having the start with the minimum 16 symbols, so it is 2 into square root of 0.4 EB. And if you have to see the complexity, so complexity is QPSK is relatively simple, QASK is relatively complex structure is there. And if you have to talk about the noise immunity, QPSK is having the better noise immunity than the QASK signal. If you have to see the error probability, so in the QPSK it is less than error probable to the QASK signal. And type of demodulation, if you have to talk about, so in the QPSK and QASK both having the coherent detection. So this is some parameters that you have to be take for the comparison, and simply write into the examination as well. So this is all about the unit number 5, but one of the more topic is that I will be just introduce you, and it will be, I will be give you the assignment to find out the more information about this technique and write the notes on this. This is a very modern technique that is used in the communication system, OFDM, orthogonal frequency division multiplexing. So OFDM is particularly well suited for high data rate transmission over the delay dispersive channels. In its own way, OFDM solves the problem of the engineering paradigm of the divide and conquer. Like a large number of the closely spaced orthogonal subcarriers is used to support the transmission. So basically this OFDM is used in the communication industry, and it is one kind of the net. So if you have to see, there is some problem networking. So it is basically OFDM is a network proposed or designed by the major telephone companies in conjunction with the Committee for International Telephony and Telegraphy, CCITT, with the intent of providing the worldwide telecommunication support of voice, data, and video or facsimile information within the same network. So ISDN is the, you can say, integrated network is there for, along with this OFDM is there. So we have to use the OFDM technique here. So in this OFDM, orthogonal frequency division multiplexing, you have to be found that incoming data stream is divided into the number of low data rate substreams, one for each carrier. Means each data stream is for each carrier, that is will be divided into the sub channel that is operating in the parallel. And if you have to be talking about the modulation process here, that is QPSK is used basically. Here in the OFDM also the modulation scheme, that is like a QPSK, it is like that. So here we have to only do the two changes instead of the regular QPSK. What is the in transmitter, an up converter is included after the digital to analog converter to appropriately translate the transmitted frequency so as to facilitate the propagation of the transmitted signal over the radio channel. And in receiver, down converter is included before the analog to digital converter to undo the frequency translation that was performed by the up converter in the transmitter. So this is the block diagram of the transmitter and receiver. Upper one is the transmitter and lower one is for the receiver. Am I audible and screen is visible to you? Someone is
Yes, sir.
text messaging. Okay. See,
Yes, sir.
so this is the structure of this that I have taken from the Simon Hacking book. Also, some similar kind of the structure is given in the top sharing book also. That is little bit simple. But you can see here the input data bit stream is given to the using a technique of forward error correction encoder that we have learned in the unit number 3. Then it would be passed through the 16 QAM modulator. Then whatever the output signal that is having the 12 megahertz, it would be given to the serial to parallel. Up to this point, output of this, there would be a analog that would be then passed to the serial to parallel converter, splitted into the sub carriers, and this sub carriers could be maybe 64 points or maybe 128 points like this. That would be passed through the FFT, fast Fourier transform block circuitry, and then again reconvert into the serial information parallel to serial converter, and then finally a digital to analog converter. And then in this way, this signal in the analog form would be transmitted over the channel. And then this signal is received by the receiver. Then again it is converted into the digital, then serial to parallel, and again 64-point FFT algorithm is processed. Okay, in the first transmitter we have used the inverse FFT, and to compensate that we have to use the FFT. Then parallel to serial converter used, again 16 QAM demodulator, and then forward error correction decoder, and finally we have to be estimate original binary data stream. You can see that whatever the blocks used in the transmitter, same has been be reversed in the receiver section. Only that the function is just in opposite manner for recovery of the signals or binary data streams. So please take the screenshot of this OFDM transmitter and receiver. Upper one is the transmitter and lower one is the receiver network user. Okay. So this is if you have to be see all about the OFDM. I have just give a very brief introduction. I know that I have not explained very in detail, but it is your, I would be give an assignment that all the other topics I have covered. This is one of the that you have to be little bit research on internet or the books and find out the appropriate information about this. Okay, so you can start to fill up the attendance. That's all for today, and this is all for the unit number 5. From next week, we will be start the unit number 6. We have very less time, but we would be covered the syllabus. Quickly fill the attendance, please. Still the 4 students are remaining. Okay, now I am going to end the meeting. Thank you.